I'm Dave Kassler, amateur extra call sign KE0OG. This series of videos walks you through the 11th edition of the ARRL Extra Class License Manual for ham radio, one section at a time. The orange shirt material, meaning the shirt I'm wearing right now, is new or modified for the 11th edition. The blue shirt material was developed for the 10th edition and has not changed for the 11th edition. I've reorganized everything to correspond to the 11th edition. Let's go! Our topic for today is section 9.1, Basics of Antennas. This section, which builds on section 6.1 of the General Class License Manual, provides quite a number of definitions that allow us to compare one antenna type with another. We'll talk about antenna radiation patterns, gain, beam width, radiation resistance, feed point impedance, efficiency, polarization, and bandwidth. That's quite a bit of stuff. With these video introductions, I'll try to provide background and a brief sketch of each subject to help you understand the material in the text. The first topic we'll discuss is antenna radiation patterns. Let's spend some extra time with figure 9-1b, which shows the radiation pattern for a simple idealized dipole. This is what's called the azimuthal pattern, and the numbers along the outside edge of the circle represent degrees of azimuth, with north at the top. In the diagram, you are way up in the sky looking down on the antenna. It's sort of like looking at a kind of special map. In this diagram, the dipole antenna is stretched from west to east. Note the words direction of dipole element. Those words go together. Now, let's take a look at the diagram itself. The outside marks a circle, marked off as though one were reading a map. So 0 degrees is to the north, 90 degrees is to the east, 180 to the south, and 270 to the west. Just like a compass would mark things out. Note that this is different from our usual convention for a circle, which has 0 at east, 90 at north, and so on. Look at the numbers here under the 0 at the top. The diagram is laid out in decibels. It's a signal strength graph. 0 dB is the outer ring and is taken as the reference point. As you move to the interior of the graph, the signal gets progressively weaker. We see minus 2 dB, minus 4, minus 6, minus 8, and minus 10. Note that with each number, the distance between the circles gets progressively smaller. So this graph is not only logarithmic, but also nonlinear. We can count down further with minus 12, minus 14, minus 16, minus 18, and minus 20 dB. Note that these circles go entirely around. For example, we can follow the minus 6 circle all the way around as shown here in green. Okay, let's see just how we read this chart. Let's suppose the transmitting ham station is situated on perfectly level ground. For example, perhaps western Nebraska, which is one of the flattest places I've ever seen. Let us center the graph over the fictional town of Flatville, Nebraska. Okay, let's go say 100 kilometers north of Flatville to Northville and put a station there. Similarly, let's put stations at 30ville, 60ville, Eastville, 120ville, and so on until we have Flatville completely surrounded. Okay, let's make a few assumptions here that aren't realistic but rather ideal. Each of these outlying stations has an identical antenna, and each has a receiver with a perfectly calibrated S-meter. Let us also assume that propagation is entirely perfect and uniform in every direction. So, here's what happens. At Northville, our receiving station registers an S9 signal coming from Flatville. Our station at Southville gets the same S9 signal. We'll use this as the reference. Now let's look at 30ville. Here we see that the signal level is about 1 dB less than S9. Moving to 60ville, the signal is 6 dB below S9. That would be a signal strength of S8. Again, note where the receiving station is, on the outer periphery of the circle, not inside the circle. The thick black line inside the circle simply represents the signal strength. Now, note that as we go from 60ville to Eastville along the track shown in blue, the signal strength drops dramatically. The signal is 12 dB down at about 75 degrees. That means an S7 signal. And as we nudge toward Eastville, our signal simply drops out of sight. In fact, Eastville receives no signal at all. You can see that this goes on all the way around the circle with full signal at Southville and no signal at Westville, and then back around where the signal is again strong. The key point I want to make here is that this is both a geographic relationship in that the degrees of azimuth are included, and also a graphical relationship of the signal in the direction of any given azimuth. Again, I mentioned that this is an ideal case. This ideal case never occurs in practice, but it gives us something to start with. Now, the point of this particular diagram is to display the radiation pattern of a dipole. You can see it has a broad pattern with sharp nulls. In practice, over real terrain with buildings and trees as obstacles, the nulls are not so sharp, and the lobes won't be perfectly symmetric. And you can imagine what patterns are like at my house here in the Rocky Mountains. Let's move into 3 dimensions as shown in figure 9-1a. This is the radiation pattern for a dipole in free space, which looks like a donut, or more precisely, a torus. Think of this as the radiation pattern for a dipole on a satellite. Here I've added the X, Y, and Z axes for visualization. Let's call the antenna axis the X-axis. The Y-axis shoots off over here and defines the XY plane, or horizontal plane. If you slice the torus along the XY plane, you get the dipole azimuthal pattern that we looked at a few moments ago in the Flatville example. In fact, note that our azimuth degrees lie entirely in the XY plane. Now, a couple things I want to point out. The Z-axis is the elevation axis. A perfect dipole radiates equally in all directions in the YZ plane, meaning a lot of the radiation goes straight up, and for a dipole in free space, down too. In a practical antenna, therefore, we must consider that not only does our radiation go forward along the Earth, but also up into the air. The book makes a very brief reference to near field and far field. All the radiation diagrams you see in this section and elsewhere are for the far field. In the far field diagrams, you can consider the antenna to be a single point. In our Flatville exercise, with the receivers all being 100 kilometers away, any HF antenna at Flatville would certainly be a tiny point by comparison. Now, when you get much closer to the antenna, within a few wavelengths, the antenna certainly isn't a point. In the near field, all the radiation is sorting itself out. Here's conceptually how it works. Each point on our dipole acts as an isotropic radiator. The circles are the waveform emanating from that point, sort of like ripples in a pond. Let's add another point a small distance away. The radiation patterns create both destructive and constructive interference, and you can see that the energy goes mostly up and down. Now let's add another point, and we see the radiation pattern focusing even more. As we add a final point here, you can see how all this constructive and destructive interference makes for a mess close to the antenna, but as we get further away from the antenna, things sort themselves out into a proper wavefront. Now actually we have an infinite number of these, and the radiation from each will either interfere with or strengthen that of the other points. So we'll mark the near field area in green here, and the far field areas in blue. Note that there is not a sharp distinction between the two. It is possible to put some math on this, but doing so is well into the realm of sophisticated antenna engineering. Just think of the far field as the point past which our antenna pattern stays the same, and the near field as the area closer to the antenna where all that power is sorting itself out. The distance from the antenna to where the far field sorts itself out is a function of the frequency and the antenna gain. Now the isotropic radiator I just mentioned is a theoretical antenna that radiates equally in all directions without any losses. If 100 watts goes in, 100 watts of RF comes out. Since there's no gain or loss, and the pattern is uniform, we say that the isotropic radiator has unity gain, meaning a gain factor of 1 in every direction. Note that the log of 1 is 0. So in dB terms, it has a gain of 0 dB in every direction. Now, there is no such physical antenna, but it can be handy as a point of reference. Now, here you see two diagrams from the book. The one on the left is the radiation pattern for the isotropic radiator, as shown in figure 9-2b. The radiation pattern is a little hard to make out in the book, so I've drawn it here in green. The diagram on the right is for the free space dipole. Note, and this is very important, these are both drawn on the same scale, so we can compare them directly. Recall that on the dipole diagram where the pattern touches the edge, it's an S9 signal. But on the isotropic diagram shown in the same scale, the green radiation pattern is a circle. It never touches the outer circle, so it's never S9 in any direction on the periphery of the circle. In fact, in every direction it's 2.15 dB lower. So now, given that the transmitters connected to the isotropic radiator and the dipole provide the same amount of power, how do we get from the isotropic radiation pattern to the dipole radiation pattern? Well, if we squeeze the isotropic in here, meaning we don't radiate in an east-west direction, that will provide power in other areas. On the upper half, we can rob power from the green areas to create power for the magenta area. The green areas look like they're bigger than the magenta area, but that's just an artifact of working with a log scale. We can do the same for the power from the blue areas going to create the yellow power. So we say that either to the north or the south, a dipole provides 2.15 dB gain over an isotropic radiator. But that is only true in the north-south direction. In any other direction, the dipole gain is less. And so how do we squeeze power in one or more directions? Well, that brings up the whole subject of antenna design, all of which is aimed at putting our transmitter power in the direction we want. It's just like this flashlight. The reflector in the flashlight aims light mostly in one direction. It's pretty dim in areas where it isn't aimed, but when I point this light directly at you, you can see it very well indeed. As an aside, let me mention something called reciprocity. An antenna that has gain while transmitting also has gain while receiving. Let's look here at the case where the station on the left is transmitting and the station on the right is receiving. Let's say that both have dipoles and the receiving station's receiver says S7. Now let's move to the case where the station on the left, our transmitting station, installs a Yagi with 12 dB gain relative to a dipole. The receiving station, still with its dipole, will receive an S9 signal. Now, let's flip that over. On top we see that we get an S7 signal when both stations have dipoles, just as before. But on the bottom, note that the far station still has only a dipole, but the station on the left receives an S9 signal. Why? Because if the antenna has 12 dB gain when transmitting, it also has 12 dB gain while receiving, and that's 2 S units. Okay, another aside. This directly addresses the question of whether to add an amplifier at your station versus improving your antenna. Adding an amplifier only helps the other station hear you better. However, it does not help you receive the other station better. But an antenna improvement helps both ways. So, improve your antenna system before you invest in an amplifier. Now, if we can squeeze power in one direction more than another, we can easily conceive of an antenna that squeezes most of its power in one direction. There are lots of antennas that do this. For example, Yagis. In figure 9-3, the radiation pattern is quite directional. Note that no matter how hard we try, we cannot squeeze all the power in a single direction. That's because in the near field, as all that power sorts itself out, some will head out in other directions. We'll learn more about this in the next video, which will discuss practical antennas. Now, a lobe is a curved section of something, sort of like an earlobe. Looking at this radiation pattern in figure 9-3, we have a main lobe into which most of the power goes, and some minor or smaller lobes. Also, very important, note the very deep nulls in between the lobes. This actually is quite important. Although it's not possible to direct all energy in a given direction, it is very much possible to construct an antenna that radiates no energy in a particular direction. It also receives no signals from these directions. These deep nulls can be handy when trying to reject an unwanted station. Now, when we measure what we call gain, we are measuring the amount of power radiated in the direction of the main lobe with respect to the amount of power that would be sent in that same direction by a reference antenna. That reference antenna can either be a dipole or an isotropic. If we use a dipole for reference, we measure the gain in decibels, referenced to a dipole, or dBd. Similarly, measuring with respect to an isotropic antenna is measured in dBi. Let's look at our squeeze diagram again. The difference between an isotropic antenna and a dipole antenna in the direction of the main lobe is 2.15 dB. Note that's expressed to 3 digits of precision. In real life, I would say that a good dipole at a half wavelength above the ground will be about a couple dB or so better than the theoretical isotropic. But be that as it may, the test questions use the theoretical gain of 2.15 dB. So, here's how it works. Let's let the x-axis represent gain, with higher gain to the right. An isotropic radiator has unity gain, meaning it doesn't add or subtract to the signal in any direction. And all RF power is converted to radio waves with no losses. Unity gain means a gain of 0 dB. A dipole has some gain in its strongest direction, about 2.15 dB compared to an isotropic radiator. Now let's put a Yagi here with 10 dB gain over a dipole, or in other words, 10 dBd. But if we measure the Yagi from the isotropic, we say that the antenna has a gain of 12.15 dBi. There are a couple of examples of this in the text. Now, let's take a look at figure 9-4 to see how beam width is described. How wide would you say this lobe is? Well, by convention, the beam width is the angle in degrees between the half power points. Half power is -3 dB. The diagram didn't have the 3 dB line drawn in, so I've added it here as the red line. I've also made note that the left-hand line going through the 3 dB point comes out at 345 degrees, and on the right-hand side at 15 degrees. So the angle between them is 30 degrees. But note something. 3 dB is a half a S unit. If we tolerate going down just a single S unit, we see that an S8 signal is to be had at 40 degrees. But we've got to use a generally agreed upon convention for beam width, and that's at the 3 dB point. But I do note that for antennas most commonly used in amateur service, beam width is only a general indication of how much your signal is concentrated. Figure 9-5 appears in some test questions and is a rather arbitrary antenna pattern with a main lobe, a back lobe, and 2 side lobes. Note here that there are no sharp nulls. Let's read this diagram closely. As is conventional, everything is measured from the peak of the main lobe. So all the dB references are referenced to the power in the main lobe, which goes off here to the right. And note here that a more normal convention for circles is followed, in that degrees are positive from the x-axis going counterclockwise. The circles in the diagram are in dB. It shows -3, 6, 12, and 24. I went ahead and drew in the -18 dB line in red. Our back lobe is halfway between -12 and -24. So we can estimate it as being about 18 dB down relative to the front lobe. By the way, that's a front to back ratio of 18 dB, which is actually pretty good. A normal HF Yagi might eke out 10 dB. Anyway, the side lobes are between 12 and 24 dB down. It's halfway between -12 dB and -18 dB, and the book says to pick 14 dB, which, as a rough estimate, is good enough. Now, the book provides 3 ratios: front to back, which is widely used, front to rear, which is something I've never encountered in 40 years in ham radio, and front to side, which works in this case, this diagram, but in the case of a real antenna, you'll probably be dealing with multiple side lobes. And I've not seen this particular ratio used before either. Now let's move to the topic of radiation resistance. The book defines it as a virtual resistance that, if it existed, would dissipate the amount of power that in fact is actually radiated by the antenna. The equation given is simple. There's the wire resistance called ohmic resistance, and everything else is radiation resistance. Yes, well, real life is not that simple. Let's take a look at an example in real life, in this case found in my own backyard. The antenna in the foreground is my butternut HF9V vertical. You can see the various traps that are used for different bands. Note the trees, which by and large are also vertically polarized, and they will absorb some of the radiated energy. There's a great big metal propane tank not far away, and a chain link fence around the dog run that's close enough to affect the antenna pattern a bit. But the biggest item interfering with the HF9V is the 22-foot long aluminum antenna mast holding up my large horizontal loop. It's close enough to react rather strongly with the HF9V. I plan to replace this mast with one made of fiberglass at some point to see how much I can improve the performance of my vertical. My point in showing this is to say that everything around an antenna, and I do mean everything, can affect antenna performance. The easiest way to look at feed point impedance is by looking at a dipole. This is quite reasonable given that the dipole is the basic unit in nearly all antennas. This diagram shows the dipole and the current and voltage distribution along the antenna, with the current in green and the voltage in magenta. No current can flow at the ends of the antenna simply because there's no place for it to go. So the current is zero at the ends. The current is maximum at the middle. The voltage is highest at the ends and lowest in the middle, in theory approaching zero at the midpoint. We recall that the feed point impedance equals the voltage divided by the current. The impedance is lowest at the middle, given low voltage and high current, and it rises as you move toward either end to the point where it is theoretically infinite at the ends. The feed point impedance depends on many factors. For example, it tends to go down if the antenna is at less than an ideal height. In real dipoles at heights common for ham radio operators, the impedance at the middle is on the order of 50 ohms, and the impedance at the end is on the order of a few thousand ohms. By the way, given that the highest voltage is at the ends of the antenna, you want to keep these up and away from anyone that might touch it. This is particularly important if you're making an inverted V. Every part of the antenna should be higher than a wandering neighbor might touch. Can you feed an antenna somewhere other than the middle? Certainly. You can feed it anywhere, even at the end. The key, of course, is to match the transmission line impedance to the antenna impedance. In ham radio, we use lots of coax that has near 50 ohm impedance, such as RG8, RG8X, RG58, LMR 100, LMR 400, RG213, and so on, which leads us to want to feed dipoles in the middle. There are other types of transmission lines available with different characteristic impedances depending on the situation. Then, of course, the feed line impedance needs to be matched to the transmitter's output impedance, nearly always 50 ohms in amateur practice. If there is a feed line impedance mismatch at the antenna, it can change the apparent impedance that the transmitter sees. That's where we insert an antenna tuner. My 80 meter full wavelength horizontal loop definitely doesn't have a 50 ohm feed point. I use a balun to help translate the feed point impedance into 50 ohms. Then I run the coax down to my antenna tuner, which connects to my rig. Let's talk about polarization. Polarization refers to the plane of the antenna's electric field, which is sometimes called the E field. Remember, we talk about radio waves as electromagnetic waves. So in addition to an electric field, there's a magnetic field, which is at 90 degrees, sometimes called the H field. In this diagram from the ARRL handbook, the direction of propagation is in the direction of the x-axis. The E field is parallel to the ground, so this waveform is emitted by a horizontal antenna shown here. We use the right-hand rule to find the direction of the magnetic or H field. We point our right thumb in the direction of propagation, then our fingers point in the direction of the magnetic field. Just as a point of clarification, waves don't wiggle through space like this. They travel in a straight line, but the graph gives a representation of intensity. Note that the E and H fields are in synchronization except for the 90-degree orientation difference. Now, and this is important, a vertically polarized antenna will have a vertical electric field, and the magnetic field will then be horizontal. So, by and large, you can determine the electric wave polarization by looking at the antenna elements. A dipole provides a horizontally polarized electric field, and a vertical antenna produces a vertically polarized electric field. Here's an example of a vertically polarized VHF antenna. You can tell the polarization direction by looking at the element orientation. Now, I want to look at figure 9-6. The book talks about this being in the H field direction. That means that the antenna in question is horizontally polarized. This drawing, which appears on the test, shows the elevation profile for the antenna pattern, meaning how much the gain changes with changes in elevation. It's like looking sideways at an amateur station and watching the beam reach into the sky. On the figure, we see that there are 4 lobes pointed in the forward direction at 7.5 degrees, 25 degrees, 45 degrees, and 73 degrees, and 3 tiny lobes pointed backward. There may be side lobes, but we don't see them in this diagram because we'd be looking at them end on. Now, this antenna is typical of a Yagi. One key definition is that the elevation from the antenna providing the most powerful lobe is the antenna's effective elevation angle. This diagram shows clearly that there's also lots of energy in the other forward lobes. Why is this important? Because the power from each lobe will hit a different part of the ionosphere and be reflected to different places. The power in the lowest lobe will likely travel the furthest, but not always. A key takeaway from this diagram is that antennas usually do not propagate directly horizontal to the Earth, but rather the energy tends to travel up a bit. That leaves us with one more topic, that of an antenna's bandwidth. Let's take a look at this antenna meter, which shows SWR as a function of frequency. By definition, bandwidth is the width of the frequency spectrum that provides an SWR better than a given reference. The book uses 1.5 to 1 as a starting point. Now, let's look at this. Almost all transceivers can handle up to a 2 to 1 SWR. We see here that the 2 to 1 bandwidth is wider than the 1.5 to 1. And many modern transceivers with built-in antenna tuners can handle up to a 3 to 1 SWR, and the 3 to 1 bandwidth is even wider. I think the key takeaway from the section on the effect of real ground on antennas is that real ground is just plain messy. And when I say ground, I mean exactly that, the earth beneath our feet. By and large, dirt, soil, and rock are electrical conductors to a small degree, but certainly none of these are as effective as a theoretical ground. If the ground were perfectly conductive, as shown in the yellow panel at the left of the diagram, a vertical antenna would be perfectly mirrored, resulting in an antenna with no ground losses. The antenna's resistance would consist solely of radiation resistance and the ohmic resistance of the wires. But real ground is not a perfect conductor, as shown in the magenta panel in the middle. The poor conductivity of the ground becomes part of the overall ohmic losses. In other words, you are literally heating the ground. So, as the ohmic losses rise as a result of the soil's poor conductivity, the overall antenna efficiency goes down, and, as shown, the main lobe angles up rather more. We compensate for this by using radials, as shown in the blue panel at the left. The radials are shown in red here. This helps improve effective ground conductivity, but they're not perfect. All vertical antennas over real grounds require radials to lower losses. This improves antenna performance and lowers the radiation angle somewhat. The only exception to this need for extensive radials is the case of seawater. Salty seawater is highly conductive and makes for an excellent ground. That is, if you consider water to be ground. A vertical antenna does not need to be ground mounted. If you mount the vertical on a mast and get it up off the ground as shown in the center, the radials need to follow the bottom of the antenna up into the air. According to the general rule that height always helps, pushing a vertical in the air also lowers the elevation of the main lobe a bit. Also, interestingly, not as many radials are needed as might be on the ground. If you go even higher, you can cut the number of radials to a couple that are resonant on each band. Note what has happened here. We've gone from lots of untuned radials on the ground to a few tuned ones in the air. I point out in passing that my first antenna as a novice was a chimney-mounted high-gain 14 AVQ vertical with a few tuned radials. It worked quite well. Now, a horizontal dipole doesn't need the radial system that verticals need, but ground still affects their performance. The dipole mounted near the ground, as shown on the left, will have a higher elevation angle. As the dipole is moved up, the elevation angle comes down, as shown in the center. The higher you go, the flatter the pattern. So the question is this: how high should a dipole be mounted? The generally accepted answer is that it should be mounted a half wavelength in the air. In the case of a 40-meter antenna, a half wavelength is 20 meters or so, on the order of 60 to 66 feet. Most of us don't have anything to get an antenna that high in the air. We all have to mount them closer to the ground. As I noted in the last video, all antennas are compromised designs, and we just mount our dipoles as high as we can get them. The book makes the key point that your station ground is an important part of your antenna system. You really should put in a real ground rod and attach your transceiver's ground lug to this. It's helpful if the connection between the transceiver and ground has the lowest ohmic resistance you can muster. The book points out that a flat, wide copper ground strap makes an ideal ground wire to go between your rig and your ground rod. Well, that's cool, but hardly ever done. Most hams use braided ground strap, which looks like this. I point out that there is a massive amount of folklore regarding how to properly ground your station. Certainly, you should not use your home's wiring ground if for no other reason than it's electrically noisy. And grounding to a cold water pipe does no good these days because most household utility water feeds are plastic. A separate ground rod really is something you should have. The book suggests that multiple shorter ground rods are the way to go. Well, it says that because a test question says that. How do I do it? Well, I do have a ground rod, which is also my lightning ground rod. To this, I attach a sturdy number 2 wire, very thick and with low resistance. This wire goes under the house and then up into my shack. It's attached to a short copper pipe, which is my station single point ground. I then use ground braid to ground each piece of station equipment. Please note, your installation will be different, but it's always nice to have something to compare to. Needless to say, there are myriad ways to compare different kinds of antennas. There's a lot of folklore out there on the subject, some of it true and some of it silly. Generally, the best antenna for you is the one that works the best for you, which could be entirely different from someone else's setup. You may have to consider the amount of space you have, which can cramp your antenna installation. Perhaps you can put up a dipole, but can't get it very high in the air. Every antenna installation, all of them, are compromises of some sort, and real antennas seldom perform the same as their theoretical cousins. This is why antenna experimentation is so popular. The ARRL's magazine, QST, devotes an issue every year to the topic of antennas. A couple rules. Any antenna is better than no antenna. Height helps, full size helps. Beyond that, a world of exploration lies before you. And that's it for this lesson. The next lesson focuses on practical antennas. This is a good time to review section 9.1 and study the test questions. This video has been updated or reorganized for the 11th edition of the manual. You can pose questions in the comments on YouTube or on my website or at www.ke0og.net/ask-Dave. If you spot an error, please let me know. Also, I ask you to subscribe to my channel, Ham Radio Answers, so you will get notification of upcoming videos. And if you're so inclined, there's a tip jar, both on my YouTube channel page and on my website. Until next time, this is Dave, KE0OG, wishing you the best in your studies, and 73.